My research involves computer modeling of water, sediment, and nutrient systems as all those components move from land surfaces through streams and rivers and into downstream receptacles, perhaps a reservoir or a lake. Each of these components can all be represented by their own computer model. But what's important is to integrate these models into a modeling system. And that way we can see the impact of nutrients from an agricultural setting or as effluent from urban or industrial sources on a reservoir or lake. These models and modeling systems require a lot of data. Now, a lot of this data is archived in various sources, for instance, climate, water quality, or water quantity data. We have to know the topography of the landscape, how that land is used, the soil type, the geology. We also have to know what the amounts of fertilizer are being applied to those land surfaces. Then we also have specific data requirements where we have to go into the field, or we have to go on the water bodies to collect water samples, for instance. Or we might have to do a bathymetric survey of the river. We have to see how deep certain areas of the river are. Much of this research with modeling systems focuses on the Saskatchewan River Basin. And the reason why we've picked that for our playing field is because of the intense agricultural activities in the catchment area and because of the strong demand on the limited water resources in that system. What I'd like to show you here is an animation of a surge from 2013 flood through the South Saskatchewan River. We're looking southwest in the catchment. These along here are the Rocky Mountains, where the South Saskatchewan River originates, through here the Oldman River and the Bow Rivers that's joined to form the South Saskatchewan River, and then the Red Deer River meets up with it and continues on until it reaches Lake Diefenbaker. The flood caused a lot of transport of sediment and nutrients through the river. We can see that here with the brighter colors through the river system. And then eventually it does enter Lake Diefenbaker. We'll see now a side profile of Lake Diefenbaker where the plume enters the lake on the left side and is transported through the lake to the downstream end, which is on the right side. We can also see that some of the sediment is transported towards the end, but a lot of it is deposited along the lake bottom. The reason we carried out this animation is to first see how long it would take for that plume, which also carries bacteria, to the far side of the lake, where we also have some public beaches. This allows us to determine when we have to go out sampling. Perhaps an advisory might have to go out if the water quality is degraded through that plume. The modeling also allows us to determine if there will be algal growth due to the increase in nutrients coming into the lake, but that sediment also makes the water turbid, so there could be shading from sunlight. So there's a balance. We'd like to know when or if we will get an algal bloom after that plume enters the lake. There could also be repercussions downstream of the river. Some of that sediment, although albeit a smaller amount than that has entered into the lake, might also be transported downstream and affect the water quality for drinking water abstraction, for instance. What I'm showing you is an averaging of the nutrient loadings over a longer period of time. We see here the lighter colors where we have a higher nutrient loading into the South Saskatchewan River system. This also provides us an opportunity to look at how things might change in the future through land use changes and climate changes. So what we'll replace our land use data sets with new data sets We have areas with brighter colors which indicate higher nutrient loadings into the river system, and higher yields of nutrients from these land surfaces. This shows us now potential hot spots in the future and provides us with management options that can alleviate the nutrient loading for the whole South Saskatchewan river system.
Dr. Lynn Schmidt and his group is working more on upstream of Lake Diefenbaker. However, downstream of the Gardner Dam and the lower part of South Saskatchewan, the river is receiving effluents from wastewater treatment plant and lagoons. We're interested to know the impact of ice-covered condition on nutrients transformation and transportation in water bodies. We're using WAS-7 water quality modeling analysis and simulation program to simulate concentrations. In this video, I'm showing you the changes in dissolved oxygen concentrations along the river in wintertime. Dissolved oxygen is relatively constant from upstream to downstream. In some cases, it decreases in a downstream direction. We have found that the river is biologically active in winter time, and nutrients are still transformed and transported under ice-covered conditions. This water quality model helps us to determine the most crucial points along the river where we need more management and monitoring. We also can foresee the outcomes of changes due to water demand or climate change. For example, the shortening of ice-covered conditions or period can cause changes in water quality of the system. The results from this study provide insight into important water quality monitoring aspects in cold regions.